Hello, and welcome back to another IB Math speedrun with me, Vince. In this speedrun, we're going to be going through Unit 5.4 of the textbook and finishing up Chapter 5. So let's jump right in. So the final things we need to know, at least for this part of statistics, is, well, lines of regression, really, correlation, causation, and linear regression. So, before we get into any of that, we need to talk about data first. So, many of the methods we've been applying apply to univariate data, which is when we're getting the certain item and we're only measuring one thing about it. Say, the first item it's 10, the second item it's 20, the third item it's 40. But this is obviously not always often the case. Normally, we would actually measure two or more things about some data. For example, if we were looking at cars, we would want to know the price of the car and maybe how fast its top speed is. And as you can see, these are more than one point of data. If it's 2 points of data, we call it bivariate data. And we often use bivariate data to look for trends or correlations between them. So how do we plot bivariate data? We need to use a scatter diagram. And what a scatter diagram looks like is it shows the relationship between two quantitative variables from an individual on the data set. So we're just getting one individual and we're plotting the data points on it. So the value of one variable appears on the x-axis and the value of the other appears on the y-axis. And so when we're looking at a scatter diagram, we want to try and see if there's any trend between the two variables. And so there are many ways we can describe the trend. The first is association. Let's put here association. So association is whether the trend has positive or negative association. In other words, if the two variables are, if one variable increases and the other variable increases, then we call it a positive association. If one variable is decreasing while the other variable increases, then it's a negative association. Okay, next, we need to talk about the form. So this is the general shape of the graph. It's like categorizing what graph this fits. And normally we want to make it a linear graph. But, of course, sometimes you can get quadratic or like some absolute value. But normally, it's a linear graph. And finally, we want to get the strength, which is how closely the points follow the specified association. For example, if we say it's a linear trend, a linear positively correlated trend, then how close are these points to this line? What's the strength of the correlation? And so this can either be weak or strong or moderate. For example, this is a very strong correlation. However, if we add some numerous outliers to this data set, then the correlation becomes much weaker. And we measure the correlation using variable r, and it measures the direction of the association and the strength of a linear relationship between the two variables. And so it can obviously be, we can say strong or weak, but sometimes we also put a number on it. And that number we normally put is called the product moment correlation coefficient. So I don't believe you need to know how to numerically calculate r or r squared. You need to be able to use a calculator to obtain this value. And of course, tell yourself whether this is weak or strong correlation. Yeah. So if we do get some data, normally the first thing we want to do is to draw a line of best fit through it. This is just by eye, just drawing, what line do we think matches this data most accurately? However, this is often very inaccurate, and so we can use a method called linear regression to find the equation of the line that best fits the data. So this is when in order to draw the most precise line, we normally use something called the least squares regression. So this is when the line passes through the points in such a way that the sum of the squares of the deviations is at a minimum. So for example, if we draw our line here, then we know that this line is in that square, it's in this square, actually other side is probably shorter, it's in this square, and it passes through this square too. So using these squares, we can look at we just want to minimize the area of these squares, which is the area of the deviation from the actual points. And if we minimize it, we will get the proper value. So if we consider the vertical deviations, so in this case, this side, then the regression becomes the line becomes the regression of y on x, so on the line y on line x. However, if we're considering the horizontal deviations here, then it becomes the regression of line x on line y. Line x on y. Normally we do line y on x, and so we would calculate the vertical regressions. And so we would obviously use a calculator to do this. So, what else? Correlation, or how strongly the points correlate, is measured in direction and strength between two variables. And so when we plot the scatter, if it shows a linear relationship, then we emphasize this by drawing a line. We should only draw a line if there is actually a relationship between the two variables, and it should only be drawn when one variable helps explain or predict the values of another variable. That's a relationship. I guess the one more thing to note is when we do classify the strength of a relationship, normally these values of R range from -1 to 1. So -1 means it's a very strong negative relationship. Negative 0.5 is like a moderate negative relationship. Negative 0.5 is a weak negative relationship. Of course, 0.25 is a very weak negative relationship. 0 is no correlation. 0.25 is a very weak positive. 0.5 is a moderate positive. 0.75 is a moderate positive, and 1 is a very strong positive. So ideally, we want to look for correlations that have the strongest possible correlation. Okay, and so finally, we need to talk about interpolation, extrapolation, and correlation fallacies. So the first is interpolation. So interpolation is when we predict a value from within the smallest and largest values. So this is when we're trying to use our regression line to predict a value within the range of the data set we have. Now, extrapolation is when we want to predict a value outside the smallest and largest values. So the accuracy of interpolation depends on how linear the data is and how the strength of the correlation, whereas the accuracy of extrapolation is normally very low because it assumes that the trend continues past the two data points measured, and so it's very unlikely to be reliable. So finally, we have to look at some correlation fallacies, and I'll go over these briefly. We need to know 6 of them. The first one is correlation versus causation. And this is the fact that because two factors are correlated, they don't always mean that one factor causes the other. And so it's unfair to say that just because we can draw a line of best fit, that one variable actually causes the other. The second one that's wrong is that correlation is only linear. And this is clearly not true. Variables can clearly be linked in nonlinear ways. In fact, most of the time they are linked in nonlinear ways. It's hard to recognize or to graph nonlinear variables by hand, but technology can allow us to do that. Third one is theory of the third variable. So this one is like assuming that there's a third underlying variable from which the two variables may be related. And so this is very important. It's very important to look at whether there's actually a third variable that's causing the correlation between two variables, or some control variable that's affecting the test. The next one is spurious relationships. And so it's essential to know, this means it's essential to know whether there exists an actual mathematical relationship between the variables, which may give rise to an invalid correlation. So there might be some, one variable might be directly derived from another, which may cause a faulty relationship. Fifth, we have combinations from separate populations. So it's essential that the data set arises from one homogeneous population rather than two distinct groups. That's pretty obvious. And finally, incorrect sampling. So obviously, if the data isn't random, then it's hard to, the correlation may not be valid. With that being said, let's move on to some questions. And so I'll do the odd ones. So the first one is to consider the following scatter plots and suggest explanations for the form, strength, and association. So this first scatter plot shows the grade in maths versus the grade in art. So what is the form of this graph? Actually, this graph does not have a form, I'd say. There's just no correlation. The strength is very weak, and there's no association between these two data points. So this is the graph for grade in math versus grade in art. And from this graph, it's not that we can't tell anything. Actually, this graph tells us that there is probably no correlation between a student's grade in math and a student's grade in art. Okay, on to the next graph. We have amount of revision versus score and test, and it's a line that looks like, well, we have a line of best fit as well and some data points here. So what is the form of this graph? The form is a linear graph. What's the strength? I would say the strength is very strong, and its association is clearly positively correlated. So from this data, we can get that the amount of revision versus the score and test is probably positively correlated. So these two factors are obviously very important to one another. Finally, we get here, temperature versus heating bill. And this graph looks like something like this. So we can see a very strong negative correlation. So association negative, form linear, and strength very strong. So yeah, this is how to talk about graphs in the sense of correlation. Okay, and let's move on to the final question. And so the final question is, cars in which are bought new immediately begin to lose their value once they are used. And then some data is given. So first, we want to draw a scatter plot to represent the data. Next, we want to determine the strength of the correlation and use the regression line to predict the price of a car that has driven 50,000 miles. And finally, state any other information useful when determining a car's value. Okay, so I already have the data here on this Google Sheet, and I actually have the regression, but I'll show you how to do that. Now, if you're in a test, normally you would use a graphical calculator. The method might be a bit different, but the steps might be a bit different, but the method's exactly the same. So this is the data. We have distance driven and the value of the car. So first we want to draw a scatter plot to represent the data. Using Google Sheets, we can press Insert Chart to insert a chart. Sorry about that, my internet crashed. Anyways, we have a chart, and we want to change this to scatter chart, so it will plot. Am I lagging? Scatter? No? Yes? Sorry, I'm back. My computer was lagging. So anyways, we have a chart here, and we want to change it to scatter, and it shows this set of correlations. So that's activity 1 done. Now determine the strength and use the regression line. So if we were to determine the strength by eye, I would say this is a moderately strong correlation. just by looking at the points. But if we have a computer, we can make it much better by using a regression line. So in Google Sheets, we have to go to series and then trend line, leave it as linear, and we use the label as the equation and show r squared. R squared is the correlation factor, or the correlation factor squared. So as we can see, our r squared value is around 0.503. So this looks like a weak correlation, maybe a moderate to weak correlation. Actually, that's r squared, so we actually have to square root that. So getting the square root of 503, 0.503 is equal to 0.7. So it's a moderately weak negative correlation. And we also need to get the price of a car that's driven 50,000 miles, and we can do that by using this equation. So we have negative 0.146 times 50,000. This is, of course, the equation of the regression line, plus 38342. And you should get a value like $31,042. Finally, state any other information that useful when determining a car's value. Well, I mean, we could obviously consider the make and model type of car, the selling price when it was new, and maybe how rare the car is. So yeah, that was all for the speedrun, and I hope to see you in the next one, where we'll sign off with the chapter review. So see you then.